Ensuring safety is essential and critical in multi-quadrotor systems. Significant challenges need to be tackled when designing a control solution, handling the complex nonlinear and higher-order dynamics of the drones, taking into account actuation constraints and also being resilient to limited communication or sensing. To solve this problem, we propose a novel optimal control framework that optimizes the motion of the quadrotors while concurrently satisfying motor thrust constraints and safety constraints with control barrier functions. We analyze the impact of a limited detection range on the safety properties of the system. We design a decentralized NMPC that calculates the optimal motor thrust of each quadrotor to track a reference trajectory. We incorporate second-order exponential control barrier functions, or ECBF, as safety constraints to keep the quadrotor safe with respect to the neighboring obstacles and other quadrotors. Each quadrotor only accesses to the teammates and obstacles relative information if they are located within a certain limited detection range. Control barrier functions are increasingly popular for providing safety guarantees to the system. However, these guarantees might be jeopardized by communication and sensing restrictions. In this work, we theoretically analyze the minimum detection range possible that will not compromise the safety properties of our ECBF. We derive a conservative lower bound, which preserves the guarantees across all pairwise ECBF, whatever the action taken by the quadrotors or their velocity. Then we derive a non-conservative bound that preserves the guarantees for a pair robot to robot or robot to obstacle, whatever the velocity of the robots. The non-conservative bound cannot guarantee the compatibility across multiple ECBF, but is enough in practice, as we will see in the following experiment. We run multiple simulations in an environment of increasing density of robots and obstacles and under various detection ranges. We test an infinite range, our non-conservative minimum bound, and also two more restrictive ranges. For each setup, we randomize the initial and goal positions of the quadrotors. As expected, the more dense is the environment and the more restrictive is the detection range, the harder it is for the robots to stay safe. The lowest range significantly increases the number of safety violations. The minimum bound demonstrates similar collision avoidance performances than an infinite detection range, which validates its efficacy. In this real-world experiment, we deploy the NMPC on 3 quadrotors constrained by 3 external obstacles. The controller runs on board and at a frequency of 160 Hz. The robots travel back and forth 5 times between initial and goal positions. At each trial, they successfully stay safe under the non-conservative minimum detection range.